Alright, we are back to 30 days of machine learning. This is day 14 out of 30. It's been a very exciting 13 days. The past two videos, very long, very heavy, and very, very mathematically relevant to anything that we'll be doing forward. For those who are new and are watching day 14 straight away because they search for anomaly detection, day 12 and 13, the past 2 days that I'm talking about, are for the PCA and autoencoders. Very crucial days, those ones as well. Okay, record over. That brings us to day 14, a very unique, a very new model, I must say. I mean, not new as per how machine learning is considered, but new because this isn't discussed as much as other options for this specific problem statement. Okay, so without wasting any time, let's get back to it. So what do we have on our hands today? We have a credit card anomaly detection problem. Okay, so as usual, we'll be moving forward with our typical way. Okay, first of all, let's quickly get into the problem statement. What do we have in this problem today? So the thing is, guys, that frauds are everywhere. Okay, there are people who take part in fraud. Then there are fraudulent values. There are all sorts of frauds in usually every industry, especially in banking, finance. This is probably the industry which has probably poured money into fraud detection models. Okay, to detect fraudulent values. So that is something that we are going to do today. So today on our hands we have a credit card dataset. You can find the dataset on Kaggle itself. All of the datasets that I use are pretty typical till now. If there's anything different about the datasets, then I will inform you about it. Okay. So it's a credit card fraud detection dataset. Okay, so there are some values which are normal. Actually, there are most values which are normal, and then there are a few fraudulent values. And we have to design a model. We have to implement a machine learning model where the model is successful in detecting the fraudulent values accurately. Okay, so uh, let's first look at the problem. So this is an unsupervised machine learning problem, meaning that no labels are present in this case. Okay, so the data set is label free. Okay, and the model must isolate the behavior, and that is how we do this. So basically we have got different features. In this case we have got 28 features. Okay, and the features are all PCA transformed continuous variables, so that the model has reduced dimensionality than the original model. Okay, it has got time and it has got amount. These are the most important features. Okay, this is the class, like again, this is an unsupervised model, so there are actually no classes in this case, but we have tried to uh, make the classes so that we can calculate the metrics later. So these are the two classes we have created. Okay, so class 0 means that the data point we are considering, the data point in question, is normal, and class 1 means it's a fraudulent data point. Okay, now moving on quickly. So we have got the data set, we have got, this is the pipeline first of all. Okay, so now let me quickly get back to the board so that we can discuss the meat and potatoes of today's problem statement, because this problem is going to have a very very new model. Okay, something which is not as popular in machine learning, but it is still very important. The idea behind it is very simple and it's revolutionary. So without wasting time, let's get back to it. Okay, so first of all, the first things first. Okay, so as I said, today what we have on our hands is anomaly detection. Okay, anomaly detection. Okay, so of course, in general terms, we can discuss. So anomaly detection, we can basically say, we have to detect the abnormal samples in the data set, right? We have to detect abnormal samples in the data set. So there are going to be some normal values in the data set, and there's some abnormal values. So we have to detect the abnormal values in the data set. Okay, we can say this. Sure, we can say this. But if we try and discuss it in a bit more technicality, in a little bit more of technical terms, shouldn't we first discuss what an anomaly is, right? So let's do that. So let me quickly get another color so that it's different, because this is pretty important. Okay, So, what is an anomaly in general? I think it's nothing new. We are all aware about what an anomaly is. It is a basic word in the English vocabulary, right? So, you must know by now what an anomaly is basically. So, what is an anomaly? We can say maybe an unusual value, right? A value which makes us question what is happening, a value that is different from what it is supposed to be. Can we say that? Yes, we can. But if you want to express this same idea in a bit more technical terms, maybe we can say that a data point which doesn't fit or conform to the geometric or statistical structure of the data. Okay. Now, what does this mean? So, it's basically anomaly, but it's the same definition in a bit more technical terms so that, it becomes relevant to our machine learning problem statement today because, this is computer science. Specifically, this is machine learning. We cannot speak like general. We cannot speak in general English. So, our definitions of certain terms need to be extremely on point. We can understand it in whatever way we want. You can put it in your mind in chunks, in any way you like. But whenever someone asks you the official definition, the formal definition, it should be on point. It shouldn't be some vague, misguided explanation. Okay. So now, of course, this looks very confusing. It's not. Let me quickly explain it what it means. So this is basically, giving the definition in the terms of geometry or in the terms of statistics. What does it mean? Let's say I've got a data set. It's always good to take an example to understand these things. Let's say I've got these points right here, right? These can be anything. They can be value for money, they can be value for salary. Okay. This example that I'm showing, all these crosses, they are not confined to today's problem. This is a random example, so don't get confused about it. Okay. So we have got these points. Okay. Now all of these points are clustered together, right? They are very close to each other. I can say that they are going to be very similar to each other as well. Why can I say that? Because they are close to each other. Similar points are often close to each other, right? Like a general statement. And let's say I have another different point, like a completely separate point right here. Okay. Now, now, which of these points is going to be the anomalous point? Simple answer, this is going to be the anomalous point. Why? Why is that? Because we can see the majority of the points, most of the points, these red crosses are clustered together in one place. They are all close to each other. Okay, they are all concentrated in one place. They are part of a dense cluster. Okay, so this is basically like the normal data. This is basically, how this data is supposed to be. This is any type of data. Okay, it can be anything. These values can be anything. This value can be anything. This is just an example. This is an anomaly because it is not fitting the geometric pattern here. What's the geometric pattern? That all of the common points should be close to each other. And since this one is far from all of the common points, from all of the points in the dense cluster, we can say that this is an anomalous point or an anomaly. Did you understand it? Simple, right? There's nothing too complicated about it. All of the data which is similar is going to be close to each other. Something which is like a very big value or a very less value, something which is completely different, is going to be very far away. Okay, it can be here as well, it can be here as well, it can be here as well, right? So this is how you can understand an anomaly in the terms of technical, whenever we talk in the aspect of technical data. Okay, so this is how an anomaly is: something which is different or doesn't fit or doesn't conform to the geometric or statistical structure of our data. Okay, so this fit, you might understand, what fitting means. It means, fitting in a group or like fitting in this cluster here. Conform, this is CONFORM. It comes from the word conformity. Okay, it basically means agreeing to everything and staying in part of a group. So it is also like a very valid English word. Okay, so you can maybe add this to your vocabulary whenever you want to explain a model later. Okay, so this is what an anomalous point is. Okay, so you got what an anomaly is, sure. Okay, now a very valid question comes to anyone's mind. So we have, if I write it down here, we have understood it very clearly. What is an anomaly? Okay, very clearly, and we have understood it in the terms of technicality as well, not just in general. Now the second question, okay, a very typical question that comes to your mind is that, just a second, is that, why, second question is, why are we detecting anomalies? Very simple. Because the problem statement's name is detecting anomalies, surely this question can come to your mind. Why are we detecting these anomalies? What's it gonna, uh, why is it that we are doing this? What advantage, what profit, what business issue is this solving? Why is it helping us in whatever way it is helping? What it is doing actually? So it's very simple. See, anomalies sometimes in some models, in some problem statements, anomalies are all that we care about. Why? Take an example of a banking data like we have on our today. It's similar to a banking data. We have a credit card fraud transaction data. Now, are all the data points fraudulent in a credit card transaction model? So let's say I have a data set. So are all of the values frauds? No, there are very few values which are fraud. Okay, but the thing is, the very few values which are fraudulent can incur tons of big losses to the organization, to the bank, to the company. Okay, and those fraudulent values are what basically cause all of the major financial issues. Because if you go to a bank and you ask them, sometimes banks sometimes they disclose it, sometimes they don't disclose it. If they are transparent with this data and you ask them, like, what is your fraudulent data percentage, like how many times has it happened that your bank branch has experienced fraudulent stuff by the customers, so that percentage or that number is going to be very small. The bank people, the employees, they are gonna say like, we experience maybe 5 6 fraud cases in an entire year. Okay, but whenever those cases happen, they lead to lots and lots of major financial losses. Okay, so why are we detecting it? Because anomalous values, okay, this is very important to understand right here, because you know we won't have we won't have the bandwidth to understand this later. Okay, so just put it in your mind very clearly right now. Okay, see, anomalous values or anomalies, okay, what they point towards is a problem. Okay, initially we don't know what the problem is, but whenever we see an anomaly, we are usually almost 100% sure that this value, okay, like I showed it right here, like this value, it is not fitting in the data where it is supposed to fit, which means there is a problem. Why? Because all of these points, all of these red crosses, all of these points right here, okay, they are being produced due to some sort of underlying pattern. So let's say I am applying a formula. Okay, so I apply a formula and I let's say the formula is something like this. Okay, let's say this is my formula that is running the model, for example. Okay, this is basically the sum of first n numbers. Okay, it's a mathematical formula. So I can run this formula for 1, I can run this for 2, 3, I can run this for as many numbers. Okay, so I'll be getting the sum of first 1 numbers, which is 1, then first 2 numbers, which is 3, then first 3 numbers, which is 6, and so on. This pattern will continue. Okay, now in this case all of the values are looking very normal, right? Because they are following this underlying pattern, this formula. Everything is clear. I can say that these values are going to be very close to each other, like 1, then 3, then 6. They are going to be closer to each other because they are following a specific pattern. Now let's say that I try to break the pattern. For one of the values, instead of this formula, I apply this formula. Okay, some other formula. This is basically the formula for first n square numbers. Okay, no need to memorize this, I'm just giving it out as a normal simple example. Now for this, if you input 3 in here, okay, if you input 3 in here, the value will be something like 3 into 4 into 7 upon 6. Okay, So if you solve this, it is going to be 14, okay, for 3. So this value suddenly for n is equal to 3, it became completely different. Okay, it's not very high or very low, but it is not fitting this usual pattern that we assumed before. So this value in this case will be an anomaly. So do you see, wherever the common data points are there, whenever normal data points are there, like this clustered dense data points are there, we can say that they are there due to an underlying pattern or an underlying formula, which was this in our case, in our example that we took. And whenever the anomaly point occurred, whenever the point separate from the dense cluster occurred, we could very easily observe it was due to the change in underlying pattern. Okay, so let's say that we have got the banking data that we were talking about, that we are talking about today, that we are discussing today. So in that case we can say that everyone is getting the typical value of credit card, whatever credit card debt that they have to return. And there are a few people who are just not fitting the pattern. Okay, now that might be due to some other underlying factor, but most of the time it points to some suspicion, which gives us an idea that those customers might be involved in some sort of credit card fraud. Okay, because that way we can sort of infer that these the values of credit card debt for some customers, they are not fitting the underlying pattern, they are completely separate from what the value is expected to be. And that is what causes an issue. So that's the intuition of why we try and find these anomalies, because anomalies point that something is different, something is an issue, because it is not following the pattern it is supposed to follow, which means that there is an issue with the data point. And in this case that data point is like a customer, because we are talking about credit card fraud. Okay, this is the reason why we try and find anomalies, because if we don't, then detecting these rare values, these anomalies, if we don't detect them, it can always carry a lot of risk, especially financial risk, and no financial organization can afford that. Okay, that is the reason. Now comes the third thing. So we have till now very intuitively discussed what are anomalies and why are we even cared about detecting them. Okay, the two major questions first of all. This is all building up intuition towards the final model that we'll be using today. Okay, now comes the third one. How do we detect them? So we have got that we have to detect them and what they are. Now begs the problem, how do we even detect them? How to do it? So the very easy, this is not even very difficult to understand. The first one I can say KNN, the KNN model, the most intuitive answer. Anyone will say KNN in this case. In fact, it should be the first thing that comes to your mind. And the reason is very simple, because KNN is distance based. I can calculate the distance between any 2 points and I can say if that point is far away, it means that it is an anomaly, otherwise it is not, right? It sounds so simple. So let's see how the KNN model will work like. So how to detect them? Maybe the first can be distance based models. Okay, distance based models. For example, KNN, there are other ones as well, but the KNN is very popular, one of the simplest ones in machine learning. So let's talk about it first. Maybe KNN. Let's say I have this point. Okay, all these points clustered together. Maybe there is another cluster here. Okay, some other pattern. Okay, and then I have some anomalous points with a different color, maybe here, here. Now what do? I calculate the distance. So whenever I calculate these distances, they are all going to be very less values, right? Because they are close to each other, all these values. And whenever I calculate something like this or something like this, okay, or maybe something like this, all of these values are going to be very large values. So maybe I can say that this is an anomaly. Whenever I find large values, it means that yeah, it is anomalous. Now this is very intuitive to think about, but this is not the correct answer here. Distance based models fail to detect anomalies, and they fail horribly. What's the reason? What's the reason? Try and think about it. What's the reason? Very simple. Now this brings us to me repeating this again. So we discussed this in detail in the PCA problem on day 12. Okay, it's very good. What did we discuss? What did we discuss? We discussed that in high dimensionality data sets, distance based models fail. Okay. So if you have not watched that video, you may watch it, or you can also just hear about what I'm trying to discuss right now. So this is a very common idea in machine learning. Okay. So it's pretty typical. So what it says is that whenever there is high dimensionality in the data set, which is the case in our data today, it has got like 30 features in the data set. Features and dimensions are interchangeable words. I explained that again with a lot of depth on day 12 in the PCA video. Okay, so whenever we have a high dimensionality data set, okay, let's say dimensionality is like k, or maybe we can represent it using d. Whenever we have a high dimensionality data set, distance based models start making no sense at all. Why? Because close distances and far away distances, they basically come out to be nearly the same value, and we can never distinguish between them. Okay, so what happens is that the near distances and the far distances, they start to look similar in the case of high dimensionality data, and that basically causes an issue because we cannot make a decision after that. So that is the biggest problem with KNN in anomaly detection. Okay, the second problem, whenever we use KNN to calculate distances, we are usually using something like maybe a Mahalanobis distance or something like a Minkowski distance in order to calculate the distances. Now, calculating distances usually requires a time complexity of big O of n square. Okay, so it is a quadratic time complexity, and we discussed the quadratic time complexity is usually not suitable anywhere, because whenever this n value increases, this whole value increases by the square. So if n is something like 4, the square of it will be 16. So the values blow up pretty fast, and they take a lot of computational time to do that. This is the primary reason why in detecting anomalies, distance based models fail, and they don't fail normally, they fail horribly. Okay, two reasons: high dimensionality, and number two, computational power. Okay, that these are the two reasons. Now, okay, that's fine. Okay, we are like, okay, we tried a model, it failed. Okay, why not go for something other? Sure, we should go for something else as usual. This is how we move forward in machine learning. We never get a definite answer in the first try. We analyze trade-offs, we pick a model, we first theoretically analyze whether this will work or not, then we have experiments. That is how we get to a definite answer. It's the correct process. So let's take another model. Maybe something like a clustering model will work. Okay, maybe it will work, maybe it won't. Let's check it out. So we have got the clustering. Okay, like a clustering based approach. So if you don't know anything about clustering, don't worry. It is not that relevant here. I will quickly discuss it so that it becomes very clear. So in what happens in a clustering based approach is pretty simple. So in a clustering based approach, what we do is we cluster or group the similar points together. Okay, so this is also pretty intuitive. It is like a very typical idea that might come to your mind. Okay, because you are saying that, let's say, these are all our common points, like the points which are supposed to be the normal ones. Okay, so all of the normal points which are close to each other will be clustered together. Okay, and any of the points which are anomalous will be far away, so they'll be not present in a cluster, and we can say whatever points are having sparse clusters or no clusters at all, those points will be the anomalies, these and these ones. Okay, very easy to interpret this one as well. नहीं नहीं नहीं, नानी काम चल रहा है मत आओ। नानी बिल्कुल मजाक नहीं चल रहा, जाओ। हाँ वहां बैठना, ठीक है, बोलना मत कुछ, माइक ऑन है मेरा, बोलना मत। Okay, so these points will be the anomalies because, well, we are not able to cluster them, right? Either the clusters are sparse, which means they're having very less values, or there are no clusters at all. It can be any one of those two things. Now, this is very intuitive. Okay, it's actually a good solution to it, but it is going to fail in the case of one very typical example. Let me show it to you. Let's say I have something like this. Okay, so this diagram is basically showing another cluster where all of the points marked with the white crosses are basically the normal points, and this red one is the anomaly. Okay, so these types of examples can exist because anomalies are usually very far away from the normal data. Like we see here, this is an anomaly, it is very far away from the cluster of normal points. This is another anomaly, it is very far away from the cluster of normal points. Now this red point here, this is also an anomaly, but it is closer to the clusters. Okay, so this type of situation can occur, and it does occur in real world data. Now in this case, the clustering based approach is likely to fail because it will say that this is a cluster, and majority of the points in this cluster are normal points. This is normal, this is normal, this is normal. All of the points except one are clusters, are normal points. So it will assume that this red point, which is actually an anomaly, is also a normal point. And that is an issue because in reality it is not a normal point, it is an anomaly. Okay, so clustering based approaches don't really work very well because they assume that small clusters means that there are anomalies, and it basically fails whenever anomalies start to arise from dense clusters like they do in this case. So this is the major issue why clustering based approaches won't work. Okay, now that brings us to what might actually work, what we try and implement in this model. Okay, so that brings us to a very important idea. Okay, let me change the color. So, till now, what are the questions that we have asked to decide our model? What are some of the approaches that we have discussed? So, till now we have discussed like how far a point is using the KNN model. We have also discussed like which cluster does the point belong to. So maybe we should change the question that we are asking so that we can get a new idea. Maybe let's try that. Let me write it down. So, maybe instead of asking how far a point is, okay, or which cluster does it belong to, can we ask a question that is it easy to separate anomalous point? Can we ask this question? Yes, we can. See, what this question is basically saying, till now we are trying to detect the anomalous points amongst a lot of normal points. That is basically the intuition of our problem statement today. See, like if I go to the original example and see what we are trying to do, this is what we were trying to do. We have got normal data, we have got anomalies. We are trying to separate them. We are trying to find the anomalies which are very few in number amongst this large data. So how can we do that? How can we try and detect that? So maybe we tried the distance based approach, it didn't work. We tried the clustering approach, it didn't work. So maybe we change our intuition altogether. Maybe instead of asking to detect an anomaly by distance or to detect an anomaly by excluding it from a cluster, we try and ask the question, is it easy to separate an anomalous point? Can we think in that direction? So it's pretty typical. Yes, we can. How? So let's say that these are again our points, dense points. These are all normal points. Okay, something like this. They're all close together, and this red one is my anomaly. This is my anomaly, or this is another anomaly right here. Okay, now let's say I try to separate these points by making random splits, random cuts in the data. How can I do that? How can I do that? Let's say I go and make a random cut in the data like this. Okay, like this dotted line here. Now, is it separating the anomalous points and the dense points? No, it is not. It is just creating two more areas where this is still dense and this is still dense. So it didn't do anything special. Maybe I can make another random cut like this. Is it separating the anomalous and dense points? Yes, it is. It has actually separated this point and all of these points all together. Maybe I can make another random cut like this, so it will separate this point and again these dense points all together. So this approach actually does work. So this approach brings us slowly towards the model that we try and use today. Okay, and this is basically based on the concept of isolation. Okay, basically, we are saying that anomalies are very few in nature. Okay, very few amongst all of the points, and they are very rare. They are usually separate from the dense data. So maybe we can try and isolate them in some way. Maybe we can try and separate them in some way. And how do we separate them? By making these random cuts. Now, why are we making these random cuts is a good question, and that is what we'll be focusing mainly on today. Okay, so let's move forward very quickly. Okay, so this is basically like the concept. This concept is called as isolation, where we are trying to isolate our anomalies by making cuts in the data. Okay, and these cuts are random because random cuts are basically better at separating the anomalies from the dense points. Okay, so now comes the main thing. uh you know what we are going to do today. So this concept of isolation brings us to the model that we are using today, and it is nothing but the property or the concept of isolation tree. Okay, it is different from any other tree that we have studied today. It's a very important model, and it's not as popular as other models in machine learning. Okay, you won't see many people discussing this model in the depth that we try and analyze it today. Okay, this is basically the isolation tree model, very important. Okay, now let's go a bit deep into the data. How is this going to work? How is this tree going to work? What's the principle? We'll discuss everything. First of all, let me quickly give you a quick revision what we have done till now, because whatever we have studied till now is important for all of the concepts that we are going to study in the isolation tree. Okay, so very important. We are trying to separate the data. We try for a distance based approach using KNN. It obviously does not work because KNN has its issues, especially with high dimensionality data and this n square blowing up. Okay, clustering does not work because of this single example. Okay, it fails to detect how far a point is, or how close a point is. So clustering also fails because it is not able to recognize an anomaly when it belongs to a dense cluster. So it fails because of that single example. Okay, there's also other issues with clustering. You can read it, but one counter example is enough to prove. Okay, so we try for some other approach. Now we change the question, that is it easy to separate the anomalous points? We say yes it is. We can make a single line and separate it. See, the probability of finding an anomaly by separating is always very high. So this is like a very successful model. If we make it properly, it comes out to be a very successful model. See, because it's, first of all, look at the simplicity, the nature of it. We are just drawing cuts, and we are saying that these cuts are not based on a formula. We are making random cuts in the data. Okay, so now, before moving forward to the depth and the physics of isolation tree, one doubt that is always there, and it's a good one. It's like, when we are making these cuts, like, we take this one, like, we have made, like, let's say we made this cut in the data. Okay, between these x values. So someone might ask that, won't this cut divide the dense points? So the answer is yes, but that isn't going to cause an issue now. See, our goal is to separate these points and these points from this whole data. Okay, now if we draw a line like this, which is separating the dense points itself, there is no issue because these are still going to be dense and these are still going to be dense. So the dense points are not affected as much by the cuts that we make. Okay, but the isolated points are, and that is what we want. See, if I make just one cut like this, then immediately I can say this and these two are separated. Then I need just one more cut. I need just one more cut. I need, where's the pen? Yeah, sorry. I need just one more cut, which is this. Only in two cuts I'm able to separate the two anomalies that I wanted to do, and immediately my model is, completed. So it's a very fast model as well. So this property, this concept of isolation, it basically is allowing us to get to our results very quickly. Okay, because the probability of separating the anomalies from the dense points is always very high when we make random cuts in the data, and the number of cuts required is also very less. Okay, that is the intuition of this isolation tree model here. Now comes the main part of the video. Till now we can say in a way it was sort of a general discussion. Okay, now we'll be delving deep into the model physics and the specifics of isolation tree. Okay, so let's get to it. Now, what is an isolation tree? Now, you must have studied decision trees in some way or the other. Some place or form you must have seen what a decision tree is, how it works, what's the principle. So, isolation tree is not the same as a decision tree. It's actually quite different, but the tree concept is basically the same. We have a root node, we create the left child, the right child, and we move forward. Okay, so how does it work? The first thing in isolation tree is that it has random feature selection. Okay, random feature selection. Okay, which means the feature that we use to make the cut is selected randomly. It can be anything. Okay, the second step we do is that we find the minimum and maximum value of the feature. Okay, so let's say we have the feature amount, okay, which is there in our today's data set as well. Let's say I take the feature of amount, okay, and I say the minimum value of amount is 50,000, okay, and then the maximum value is 50 lakh, okay. Let's say it can be anything. Let's say so this is my minimum and maximum value. Now to create the split, what I do is I take any value between these. I take any value between these two. Okay, so it's like if you want to select it, if you want to write it in formal terms, you can say, select any value between this range right here. Okay, any value between them. Okay, and then what do we do? Then what do we do? We create a split in the model based on that value. So how do we do that? Let's say I select a value between 50,000 and 50 lakh, and I choose the value 5 lakh. I choose this value. Now, how is the split going to look like? So it will basically ask the question, whichever data point X is less than 5 lakh, it is going to the left. Okay. And whichever data point is greater than equal to 5 lakh, it is going to the right. This is how it is going to create the split. Okay, so now if you want to visualize this in tree form, let's say that this is the root node of the tree. Okay, this is basically the feature that we have got on our hands, which is going to be used to create the splits. Then this feature root here, which is represented by the root node, we assumed it to be amount. Okay, so you take the maximum and minimum value of amount, which is let's say 50,000 and 50 lakh. Now the model selects any value between these randomly. Okay, there is no algorithm here to select the values, there is no optimization, there is no formula, there is nothing. It cannot be predicted. It is a random value between these two. It can be anything, I don't know what it is. And then based on that it will create a split like this. Okay, so let's say the data point, we have some data point X here. If it is less than 5 lakh, it will go to the left, this left node right here, the left subtree. And if it is greater than equal to 5 lakh, it will go to the right, which means the right subtree. This is how it is created. Okay, so now it is very obvious to observe the differences between this isolation tree and a decision tree. So in a decision tree, this randomness is never there. In a decision tree, what did we do? We had algorithms. We had ID3 and CART algorithm. We used to calculate Gini impurity, okay, or entropy. So Gini impurity was like, if I remember correctly, it was something like this: 1 minus p of I square. P of I was the probability. This was Gini impurity. Then I think P log P was the formula for the entropy. Okay, and based on the values of entropy or Gini index respectively, we used to calculate how we make the splits in the node. Now in the case of isolation tree, this is the new thing in this model that we are discussing today. There is no formula to do this. There is no Gini impurity formula, there is no optimization trick, there is nothing. It is all random, and that is the advantage of it. Okay, so I'll discuss it in a second why this randomness is very strong, but just memorize this very very clearly, because it is what the entire model is based on. Okay, so if I write it clearly, okay, 3 points, very important ones. Splits are not based on calculation. Okay, we saw that. See, there was no calculation involved. Now we took the maximum value, we took the minimum value, and we said to the model, you can pick any one of them. The model has no idea what it is going to pick. It picks any one of them. We can never know what it is. That is why it is called as random splitting or random splits. Okay, so splits are not based on calculation. Number two, splits are random. Okay, which I just said, the splits that are being created in the tree are random. Okay, number three, number three, okay, random splits are very powerful. This is super important. Okay, so what we are going to do now is that I am going to explain why random splits are very powerful, and I'm going to do it in three different ways so that it is absolutely clear. I will tell you the theory why they are very powerful, I will show it to you in mathematical terms, and I will show you the example as well. Okay, so random splits are very powerful. Now we are moving forward towards why this is the case, but first of all I need you to sort of memorize this. Okay, random splits are very powerful for anomaly detection, and that is the principle of the model that we are trying to use today. Okay, clear? So moving on, moving on. How do we do this? How do we do this? Very simple. First of all, I'm going to give you an example like we did before. Okay, let's say this is my cluster of points, typical points, and this time I'll make the example more interesting so you like it. Let's say that these cluster of points are representing the average marks of students in a class. Okay, so these are all different marks of students that they have achieved out of 100. So I'm writing here marks out of 100. Okay, and let's say that the teacher set a very difficult exam, and the teacher expected that the professor expected that the average marks are going to be somewhere around 50 out of 100, near about, which means that the teacher expected anywhere between 40 to 50, 40 to 60 is going to be the marks of usually all of the students, because the exam is very 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 difficult. Okay, but of course there are going to be some students which are going to have very high marks, and some which are going to have very low marks, right? Some of the students are not going to really fit in the pattern, fit in the prediction of the teacher. Okay, so those values can maybe look like this can be like a completely separate value, this can be like a completely separate value. So why are these two values separate from this one? Why are they not close to this one? The very simple reason is because they are different values. See, this is maybe the marks here are, just a second. Okay, maybe in this case the marks here are nothing but 75 out of 100. The student has excelled in the examination too much. Maybe for this case the marks are even higher, they are 85 out of 100. Whereas most of the students are concentrated around 40, 50, 52, 47, 43, 38, 51, and so on. So do you see the basic intuition here? What is the point of this isolation that we are doing? Now the thing is that since these values are completely separate, now if I ask you to separate these values, okay, forget all of the model, forget this problem. If I ask you that, these students have achieved very high marks. Oh, sorry, this looks like a 2. This is a 1. Okay, I tell you, these two students have achieved very high marks. I want you to separate them from the other. You will say, okay, draw a line between them, right? Most of the marks are concentrated around this cluster right here, and the two anomalies are here. Now forget all of the models, forget whatever we are discussing. I just ask you that, you have to separate these two students which have got very high marks and these students which have got the expected marks. So how will you do that? You will say, draw a line between them. That is the simplest way. Now you'll say draw this line between them. On the left side we have the typical marks, the marks which are normal, and on the right side we have the two students who have the abnormal marks, who have the marks which do not make sense, right? So this is the first intuition point here. This is why it works here. Okay, so this random splitting of creating a line anywhere randomly to separate the data works very well because the anomaly points are few and different. Okay, this is a very very important thing to understand, and I will be repeating this throughout the video because this is the core of any anomaly detection problem. The number one property of any anomaly detection problem is that it needs to remember that anomalies are few and different. Okay, so store this in your mind. This is like a rule. Okay, anomalies are few and different, very important. Okay, this is why anomalies are anomalies. Some Okay, so this isn't even a questionnaire, but if someone asks why are anomalies few, okay, so anomalies, it is the definition of an anomaly to be less in number. Okay, if there are too many in number, they will be like the normal data points. See, like in this case we are saying this and this is the anomaly because they are very few in number. There are only two of them, whereas most of them are similar, close to each other and lying in this dense cluster. Okay, so two properties are about anomalies, very important, which drive any anomaly detection problem. It is that they are few, we can see only two values, and they are different. See how far they are from each other, which is why they are different. Okay, so this is the number one reason why random splits are very powerful. Because the anomaly values are few and different, random splits always and always have a higher probability to separate them. Okay, and I think I showed you a dense example as well. Let's say that this is the first split that I created, so it immediately separated the anomalous points from the normal points. Let's say this wasn't the first split I created. Let me erase this one. Okay, let's say that the first split I created was let me take this one. Okay, let's say the first split I created was here. Okay, now this is still fine, this is still fine, this doesn't harm the model in any way, because once we create the split we can still say that these points are dense and close to each other, and these points are dense and close to each other, and we can say that they are still having similar values. Okay, so still we can say that this is not an anomaly. Okay, then we make another split. Let's say this time we make a split like this. Still it is not going to be a problem because still all of these points in the four different places, they are still very dense points. Okay, so these dense points, they are not affected by the splits. The issue is that the anomalous points are affected with these splits, which is why it is easier to detect them with random splits. Okay, that is the number one reason why these random splits are very powerful. Okay, now the second reason, so first we got the first reason, this is like the geometric explanation for it. Okay, the second reason is the reason of bias or the reason of unbiased partitioning. Okay, it is also a typical reason. The thing is that we know that anomalies are few and different, but do we really know about the true anomaly structure? Okay, like I showed you this multiple times using an example because I'm trying to explain, but I don't actually know whether this is the distribution of anomalies. I don't actually know whether this value is lying here, it might be lying here, it might be lying here. I don't know how the distribution truly is. I know that there might be two anomalies, there might be five anomalies, I might know the number, but I am never going to be sure about the distribution. Okay, so since we are unaware, let me write this, this is an important one. Since we are unaware about exact distribution of anomalies, our splits may lead to bias. Okay, so this is a very typical point. So let's say we were not using the isolation tree model here, we were using decision tree or something else, where we have a formula to calculate the splits. So it is going to cause an issue, because decision tree and others, formula based splitting models, they usually assume some sort of underlying structure. They assume that this is how the anomalies are going to be, this is how their distribution is going to be. But the true thing is, we don't actually know anything about the anomaly structure, so we can never be sure. And assumptions usually kill in machine learning models. We are supposed to assume nothing, because the data can be having any sort of distribution. And if we use the incorrect type of data, or if we use the incorrect type of model which is not suited to that distribution, then the results will be horrendous. So there is no point. Okay, now this is solved by typical what we are doing till now, random partitioning. Okay, why? Because random partitioning is random, so it guarantees that there is no bias. Random partitioning prevents bias. Okay, this is like the second advantage, or this is like the second reason why random partitioning is very powerful here. The first one is the geometric one that I gave, which is due to this point right here, the geometric reason that the probability of separating these values will be easier if we are making random splits. That's the first reason. The second reason is because random partitioning will prevent bias. Because it is random now, the meaning of random is that we cannot select anything, we cannot discuss anything, we don't know anything. So that is the thing that is happening. Okay, now one very important thing that you should know. Okay, isolation tree exploits geometric density of data. Okay, very important. So this is nothing but like a very important statement of it is like a conclusion of what we have discussed till now. Okay, so this statement too, you can verify it by looking at the example that we discussed. Because what we have done till now is exactly this. We have exploited the geometric density of data. Okay, we are saying this data is dense, so it is going to have all the normal points. This is not dense, this is not dense, so there is a higher chance that these are the anomalies. Okay, and since I want to separate them, how do I separate them? By making the random splits. Okay, that is what isolation tree model is trying to do. It is trying to exploit the geometrics of the data, the statistical distribution of the data. That is the intuition on which this model is based on. Okay, now there are going to be two more reasons why random splits are powerful. So another reason is because of the existence of dense clusters. Okay, so this is another typical reason, and you already know about this. So the existence of dense clusters. So as we know that most of our normal points are going to be in dense clusters, right? Most of the normal points are going to be clustered together. So like I said that if we were using any other model which creates splits, something like even a decision tree, then the splits created in the dense clusters are going to affect the dense clusters. But in our case, if we make a random split that is creating two separate parts of the dense clusters, they are still dense, and it is not going to affect the model. So any split that we make which is a little bit incorrect, it is not going to affect the model as much. Because if we discuss this example, let's say we have got this dense cluster right here, and I go on and make a split like this. Okay, now I've got two different clusters. I've got this dense cluster and I have this dense cluster. Now is this going to make a difference? No, because the model will still know that no anomaly lies in both of these points. The anomaly will be something like here, because when it will make the correct split, which is something like this, then it will understand that this is where the dense clusters are lying and this is where the sparse cluster or the isolated point is lying at. So this is why the existence of dense clusters also lead to our random splits becoming very powerful. Okay, very important. Now, let me quickly show you another example to clarify, why this usually works very well. Okay. So now we come to the path length discussion. Okay. Or like the distance discussion. Okay. So, since we are creating random splits here, is there a way to estimate whether we'll find the anomalous point first or whether we'll find the dense points first? Okay, what do I mean? What I'm saying is, let's say this is how the isolation tree is going on its business. This is the first node, the root node of the isolation tree. Okay, I take a feature, then I do the whole algorithm that we discussed, and I make the left subtree and the right subtree. Okay, then I again create splits in this, and we go like this. Okay, this is for the right subtree. Okay, then again I increase this and go like this. This is how the tree is basically going to scale, the isolation tree. Correct. Now, there is a chance that we might find an anomaly point here. We can find it, right? We can find it here. We can also find an anomaly point here. We can also find an anomaly point here. So how do we decide what is the correct point? How do we basically move forward with the algorithm? Because we know that we are creating the splits. Okay, see, if I go back to what we discussed in creating the split, see, we discussed these 4 points, right? We pick any random features such that maybe we picked amount, then we took the maximum and minimum value of amount, let's say 50,000 and 50 lakh. Then we selected any random value between them, and based on that value we created the split. Okay, this is how the split will look like. But how are we deciding the anomalies here? Okay, this is the split to make the tree, but this is not the split, this is not the threshold to decide which point is the anomaly and which point is the normal. How do we do that? We do that using the concept of path length. Okay, very interesting concept, very important as well. This is what the whole model is based upon. Okay, so to discuss path length we need to go to a bit of binary tree theory. Okay, so this isolation tree is basically, it grows similar to a binary tree. Okay, we can see that it is even looking similar to how a binary tree scales, so they are similar in concept, so we can use that concept as well. Okay, now, what is the path length for this node right here? The path length is nothing but this. Okay, so it's like 1, 2, and 3. So we can say that the path length for this node is 3. Sure, we can say that. What is the path length for this node right here? It will be 1 and 2, right? It will be 2. Okay, so we are getting different path lengths for all the external nodes. Okay, so these nodes, this one, the nodes which have no children are called as the leaf nodes or the external nodes. Okay, this is typical binary tree theory, so I'm not going deep into it. Just remember that the nodes which are at the end, which have no children, they are called as the external nodes or the leaf nodes. Okay, so how do we use path length to decide which one is the anomalous point and which one is the normal point? So it's very simple. As we discussed before, the probability of finding an anomalous point is high whenever we make a random split. Okay, so if I write it down, anomalies are found quickly and have a shorter path length. Okay, so this is very important to understand, and it's simple as well. The thing is, guys, we are using the concept of random partitioning. Okay, where we are using random splits to create partitions in the data. Now, as I explained, in that case there is going to be a high probability to find the anomalies very quickly, because we only need one correct split in order to find whether our anomalous points have been separated or not. See, like I showed to you in this example, you can create as many splits as you want in this dense data. It is going to not harm the dense data at all. The dense data will stay untouched, because no matter how many cuts you make in the dense data, it is still dense. But if you make any cut between this dense data and between this anomalous point, it will immediately separate them. So we only need one accurate split in order to separate these points. Okay, so can we say that the anomalies will have a shorter path length, which means that they will be found first? Yes, we can say that. Okay, so look at this tree example here that we made. So if this is the left subtree and the right subtree, there is a very high chance that the tree which is having the shorter path length is going to have the anomalous values, which means that this point right here, change the color, this point right here, this point right here, these two are very likely to be normal points. Okay, normal points. There is a very high probability these are normal dense points, and there is a very high probability that these points are anomalies, these ones. Okay, what is the reason? Because their path length is shorter. Okay, it means they have been found first. That is the intuition here. Okay, so the path length is the key in determining whether the point is a normal point or if it is an anomaly. Okay, so I'll again try to clarify this with an example. We'll take our typical example. So we have got a large dense cluster here. Okay, lots of points in this cluster, they're all similar to each other, right? I've got this massive cluster in this case. And then on the other hand, I've got a few anomalous values. Let's say one is lying here, one is lying here, one is lying here, another is lying here. They're completely separate values from the normal data. Now I go and say to my model, okay, find me the anomalies. The model will say, okay, I'm going to create a split based on a random feature, and the split will be also random, which means the first split can be anywhere, the second can be anywhere. So the first can be here, second can be here, third can be here, fourth can be here. Now, do you see how easy it is becoming to separate these points because they are so far away and they are so few in number? Just using 3-4 splits, we basically separated all of our points. Okay. Now, after this, the model still keeps, creating all of the splits. So maybe it will make another split like this, another one like this, another one like this. So now it is only separating. Now it is only splitting the dense data. Okay, so it is taking a longer time to find the dense data, okay, and a shorter time to find these anomalies, which is why the path length is going to be longer for the case of normal points, because normal points are a lot in number. They are going to take a lot longer to cover. The anomalies are few, and the probability to find them is very high, which is why they will be found very quickly. So whenever you see a shorter path length, it means that the point is most probably an anomaly. Okay, that is how we do for the anomalous and non-anomalous points. Okay, very important. Now comes a bit of the mathematics. The mathematics in isolation tree is very less, but it is still important to discuss. It's pretty simple to do, to be honest. Okay, so first of all, very important thing, whenever we make the isolation tree, okay, so we have got the isolation tree, we require some samples, right? Just like we require some samples to create a decision tree. Now the rule of isolation tree, this is not like a rule, but it's like a very common thing to do, and it is usually done in real life as well. We never take all of the n samples to make the tree. N is some large number. Let's say like today's data set. In today's data set, we have more than 10 million samples. Okay, we don't take all of the 10 million samples together. We consider a very small value compared to n. Okay, something like a subset value. So this in this case is being represented by this variable. This is the Greek symbol psi. You can use some other variable as well. This is the typical way to represent a subset size, which is why I have taken this. So in this case, we are taking 256 samples at once. Okay, and then we basically do the whole algorithm and create the splits. Now, we discussed that the path length is basically responsible It is basically the main measurer of whether we are deciding that the point is an anomaly or a dense normal point. Okay, so we need to discuss mathematically what does path length even mean. So first of all, can I say that depth of external node isolating a point is called path length. Can I say that? Of course I can. What else were we doing here? That is exactly what we were doing here. I told you all of these nodes which have no children, all of the nodes on the end, they are nothing but they are called as leaf nodes or external nodes, and they are all splitting. They are all splitting either the dense points or the anomalous points. So these, they are basically the nodes which are used to isolate points. They can be anomalous points, they can be dense points as well. So that is the definition of path length. Now let's say path length looks like this, h of x. This is the way to represent path length. Okay. So one very important concept which I should have stated before. So this is basically all of the physics that we have discussed for an isolation tree. But as we studied a decision tree model, a single tree overfits very easily, and the interpretations of a single tree are not usually trusted because it is very shallow, and it is not usually complex enough to find the underlying patterns, which is why we use an ensemble of trees, something like a boosting or a bagging model, where we discuss random forest as well. That is exactly what we do here. We never use a single isolation tree model. Rather, what we do is we use a collection of isolation trees, which means that there are many isolation trees being used in our current model. Okay, and that basically brings us to an isolation forest model. Okay, which is the heading of our problem statement. So we finally have arrived to it. Okay, so this is how we get to the isolation forest problem statement that we are implementing. Okay, so it's the exact same as an isolation tree. It's just that there are many trees here. So let's say there are collection of n isolation trees. Okay, so hx is the path length for one of the trees. What about the average path length? Because there are n trees, so there are going to be n different values for path length. There is going to be h1, which is the path length for the first tree, h2, h3, and this is going to go all the way till hn. So what is the average of all these values? Because I cannot take a single value, so how do I take the values? I basically average them. So this average is basically called as the expected path length. Okay, expected path length, and it is nothing, it is the average. So if I write the average for t different trees, so this is how we write it. Expected path length, e is the symbol. Okay, 1 upon t, the typical average formula or the typical formula to calculate the mean, and inside we have got hi of x. X is basically the point which is being split apart and separated, isolated. Okay, so this is the formula for expected path length. This is how we calculate the expected path length, which is eventually used to solve our model forward. Okay, now comes an issue, very very simple issue. Okay, so let's say that we calculated the expected path length, we did all the calculations, and we got the expected path length as 8. 8. Okay, simple. So what does 8 here mean? If we get something like 8, it means that the average number of path length, the average path length to basically isolate this point x is 8. So is 8 a large value or is 8 a small value? We don't know. Do you understand my point? See, first of all, let's try and interpret this value that we have gotten. What it is saying is average path length to isolate point x is 8. Okay, we don't know what point x is, we don't know what this x is. It might be a dense point, it might be like a normal point, it might be an anomaly, we don't know yet. We don't know yet. We have no way to decide that yet. We will have a way in about 5 minutes, but till now we don't have a way. So we cannot interpret this 8 value now. See, what this statement is saying is that okay, you calculated everything and you found that the average path length, which is required to isolate this x point, is basically 8. But how will I decide that this 8 value is high or low? I need something to compare it against. Do you understand? See, let me quickly get back to what we just discussed. Okay, right here. See, what I wrote was anomalies are found quickly and have a shorter path length. Okay, so what does this shorter mean? It means that it is shorter to some other path length. So I have to compare it to another length. Na? When I am getting this value 8, how can I say this is shorter when I have no baseline to compare it against? I need something to compare it na, to say whether it is whether 8 is a high enough value or whether it is a low enough value. Because let's say that my sample size was 1 million. Okay, let's say 1 million was my sample size. Okay, and now I say that okay, my average path length is 8. Now 8 for, if we have got the path length 8 for a sample size of 1 million, it definitely means that x is an anomaly. Okay, but let's say that my sample size was 16. Now if my sample size is 16 and my path length is 8, then 8 is not an anomaly anymore. 8 is a normal point. Okay, so this is a major issue because we don't have context here. We need to have some sort of baseline which we can compare with in order to decide whether the point is normal or an anomaly. So how do we find that baseline? That brings us to the formula of anomaly score. Okay, so the anomaly score formula basically helps us decide whether a point is normal or anomalous. It's like a simple formula. So the anomaly score formula, it looks something like this: 2 to the power expectation across all the trees divided by Cn. This is the formula for anomaly score. Okay, don't worry, I'll be explaining everything about it. So first things first, we'll discuss what we have studied, then I'll open up the Cn and tell you about it. Okay. Why is the E of hx here? Because the E of hx is the expected path length. I told you the path length is the primary thing in deciding whether the point is anomalous or normal. If the path length is shorter, it means it's an anomaly. If it's a very very long path, it means that it will be a dense point, because dense points are larger in number, and the process to make the tree will continue, and they will basically be creating splits in the dense points. The anomalies will be separated far long back. Okay, why are we doing this 2 to the power this? So this is very simple. Basically, having these two values in the power of 2 to the power something, this basically reduces the anomaly score between 0 and 1. Okay, anything that we calculate, this whole thing, any value you can give to this numerator e to ehx and this denominator cn, whatever you calculate, the value will lie between 0 and 1. And anything between 0 and 1 is very interpretable. Whatever it is close to 0, it will be a less value. Whatever will be close to 1 will be a higher value. So this 2 and so these values are taken in the power of 2 to squash these values, to make them easier to interpret. That is the reason. Okay, now comes our main thing, which is this cn. We need to understand this in depth. Where did this come from and what is it? So just above I discussed that we need a baseline to compare. We need a baseline so that we can establish whether this e of hx value is large or small. So that baseline is this cn. Okay, I'll tell you what it looks like, but first just look at it. So this cn, what it says, this is the expected path length, okay, under purely random partitioning. Okay, so this is like the baseline value that we compare against. Cn is basically saying that I am the average path length when the splits that we are creating, when the partitions we are creating are completely and purely random. In that case, whenever we make the splits and we achieve a path length C of n, I am that value. And if you want to calculate whether or not your point is an anomaly, you have to use me. That is how it happens. So how do we interpret this? So it's very simple. So we have got this formula, 2 to the power negative of e of hx. Okay. In the denominator we have cn. So we basically get three cases. The first case is whenever our calculated expected path length points to cn, which means it is close to cn. So these two will become equal. So it will be like 2 to the power minus of nothing but 1, 2 to the power minus of 0, right? Because e of hx and c of n are basically equal. If they are equal, they will get cancelled. So it will be like 2 to the power minus 1, which will give us 1 upon 2, which is 0.5. So 0.5 is the middle value between 0 and 1. As we discussed, the score, anomaly score, can lie between 0 and 1. And since it is in the middle, 0.5, it means that this is a normal point, like a typical normal point. So whenever we get this anomaly score, we can say it is nothing but a normal point. Okay, simple. This is the case one. This is the middle case. Now for the extreme cases, whenever our expected path length is very, very small, which means our expected path length points to 0. Okay, it is like a very small value. In that case, this formula will basically look like 2 to the power minus 0, which is like 2 to the power 0, which is 1. So the anomaly score of 1 means that it is definitely an anomaly. It is definitely an anomalous point. Okay. Now the third extreme case, very simple. If our expected path length points to a very large value like n minus 1. Okay, so n minus 1 here means that we have got n samples used to make the tree, and our path length is n minus 1, which is huge. It means that our root node has almost traveled to the end of the tree. So if there are 256 samples that we are using to make the tree, if n is 256, then we are saying that if our expected path length comes out to be 255, so it is a massive path length. Okay, so we have traveled almost the entire tree. Okay, so in this case, what's going to happen is that the anomaly score S is basically going to be 0. And in this case, we can say this is like a deeply normal point. Okay, so a deeply normal point means that it is the part of a very, very dense cluster. Okay, so this way we can conclude this is a deeply normal point. When we get the score as 1, we can easily conclude it is an anomaly, and zero point 0.5 means it is a normal point. It is not a deeply normal point. It is not part of some very, very dense cluster. It is still part of a cluster which is pretty dense, and hence we can conclude that it is a normal point. Okay. Now, we have the last thing remaining, which is where did this Cn come from? So first of all, a quick revision. Okay, so this S right here, okay, I didn't write S. So this anomaly score, it is represented as S. So you can write it as S is equals to this value. Okay, S is the symbol used to represent it. Okay, this is how it's written. This is the formula for anomaly score. Okay, so we have got two thresholds in this model here. The first one was to decide the splits, which is a random value. We like pick a feature like amount, we take the minimum and maximum value, choose any value between them, and then create the splits randomly. The second threshold is this formula, which is basically used to determine whether the point is anomalous or not. Okay, now comes the main thing. Where did this C come from? Now that is part of a very, very interesting derivation. We will not be doing the entire derivation because it involves harmonic series and telescoping sums. It goes into pure math, simplification and algebraic math. There is no need for this, but we do need to understand where the Cn came from. So let's discuss it quickly. Okay. So, when we talk about the Cn, what did I say that the Cn is basically? The Cn is basically saying, that I am the expected path length whenever pure partitioning occurs, right? So expected path length when purely recursive partitioning occurs, right? Simple. So how do we do this? How do we calculate it forward? Like, this I will show you like a neat mathematical trick. How do we move forward? So first of all, like we discussed, an isolation tree basically scales like a binary tree. Okay, why? Because it has got the same typical pattern. We are not making the nodes based on some formula, so we can easily conclude that it is scaling like a binary tree, right? So let's say that, how does a binary tree scale like? Let's say there are n nodes in a binary tree. Okay, so there are n nodes in a binary tree, let's say. So how does a binary tree with n nodes look like? What happens in it? Uh, we basically get a root node, right? We basically get a root node. Now after the root, how many nodes are left? N minus 1 nodes are left, right? Why? Because one of the node went on to become the root right here. Okay, and now these n minus 1 nodes have to be divided again into the left subtree and into the right subtree. Correct? So how do we do that? How do we do that? Maybe we can do it like this. Maybe we can say it can be I minus 1 this side, right? Maybe we can do that, and maybe we can say it is n minus I this side, where I is any random variable. Okay, so one of the n nodes went to become the root, and the other came here, and the other came here. If you add these three up, let's see if we have done it correctly. If we add these three things up, what do we get? We get n back, which means that this split is correct, right? So this basically, I'm trying to show this to you as an example for the calculation we are doing forward, that this is how we can split nodes in a binary tree. So if the first node is going here to become the root, the other I minus 1 can go here, and the other n minus I can go there. Okay, and I here can be any number. Basically it is being used as a variable in order to separate our left and right subtree. Okay, now as we started, we have got n nodes in the binary tree. We have got n nodes. Now which one can be the root? Out of all the n nodes, we have got n random nodes. Which one of them can be the root? The answer is anything. Okay, so any of the n nodes, if I write it down, any of the n nodes can be the root. Any one of them can be the root, which means the probability for a node to be the root node is 1 upon n. Okay, just I was giving this as a fact. We are not going to be using this, but the probability for any node to be a root node is 1 upon n. Okay, so whenever I decide that I've got a root node on my hand, can I say that the cost of deciding the root is something like n minus 1? Can I say that? Can I say that? Yes, I can. Why can I say that? So for this, we need to understand what is the cost of a binary tree. Like whenever we are talking, what is the cost of a binary tree? So the cost of the binary tree is like, the cost to make the binary tree, right? The cost to structure a binary tree. So what is the cost here? So, if I have made the root node right here, after that, the root is responsible for making the left subtree and for making the right subtree. Now, since I've taken one node out of n in the root here, how many nodes are left? N minus 1 nodes are left, right? N minus 1 nodes are left, and those n minus 1 have to be distributed on the right and distributed on the left. So can we say that the cost of having the root is nothing but this n minus 1 right here? Can we say that? Yes, we can. So if we are writing the cost of the binary tree, the total cost of the binary tree, can we say first of all we include the cost of the root, which is nothing but n minus 1? right? We can say that. And the job is not over yet, because we have to consider the cost of the left and right subtree as well. Okay, so how do we consider that? So, like in this example itself, we have one of the nodes here and we have to divide n minus 1 in left and right. So can we do it like this, like we did here right now? Yes, we can. So maybe I can take my left subtree with I minus 1 nodes. I can, right? I is any number here. And I take the right with n minus I nodes. Can I do that? Yes, I can definitely. Now, can you calculate the cost of this left subtree and this right subtree? Yes, we can. We definitely can. Because in the left subtree, we are going to create another split later. Then another split later here. Another one here. Okay. Similarly, we are going to recursively increase this tree. This is how we scale a binary tree in general. So what is going to be the cost of the left subtree? It is going to be nothing but the path length of the left side. And what's for the right? The path length of the right side. Correct? Can we say this? That this is the cost for the left subtree and the right subtree? We definitely can. Okay, so if this I was our root here, okay, any root here, any root value, and if this is the division on both sides, we can say that this is the cost of having the left subtree and the right subtree, basically the path length on both sides. Now, as I said, this I is any node, any random node. We don't know which node it can be. Okay, so the probability of this node I being any random node is basically 1 upon n. We discussed this above. So if we try to write a general formula for the total cost, can we say it is going to look like something like this: n minus 1 for the root node, and then a total of the left subtree and the right subtree, okay, which is nothing but the path length of the left added to the path length of the right. See, very intuitive, right? Can we say this is it? Yes, we can say this is it. And this is eventually what we try and calculate further. Okay, this is what it becomes. Now, the thing is, binary trees are usually symmetric in nature. So for ease of calculation, we try and assume that this left subtree and this right subtree has an equal path length. So instead of this very long term, what we can actually write here is 1 upon n summation of I is equals to 1 to n, and here I can write 2 multiplied by p of I, where p of I is basically the path length of any one side, and that is what we are assuming for both of them. So when I add p of I to p of I get 2 into p of I. Okay, so my final formula for the total cost of this binary tree, for the total path length of this binary tree, it looks like n minus 1 for my root, and then this value right here for the left and the right combined. So this is what comes out to be. Okay, this is basically like the path length or like the total cost for this binary tree scaling. And why are we talking about a binary tree? Because it is scaling similar to an isolation tree. Okay, so this is what we calculate. Okay, now the thing is, we can solve this further, but it is like a 4-page derivation from this point forward. Okay, I'm not over exaggerating. It is a very complicated, purely mathematical 4-page derivation. Okay, arriving to this Cn value. Why did we do all this right now? Okay, remember this. Why are we doing all of these long steps? This is basically to calculate the Cn value that we talked about right here. This value right here. Okay, but there is no point of doing all of that calculation, so I'll write the results straight away. When we solve all of this, it's using a few results from the harmonic series and a few results from telescoping sums. You can try it out if you want, just for the sake of interest. I have left another article in the description where they solve this end to end. You can look at it if you want to, if you're curious, but it is no use. The main thing is understanding what this Cn basically means. So when we solve it out end to end, when we complete the calculation, what we get for Cn is 2h into n minus 1 minus 2 n minus 1 upon n. Okay, this is the value of Cn that we get. And remember, what is Cn? Cn is nothing but the baseline value. Okay, if I write it again, Cn is the baseline for what normal looks like in an I tree. Okay. So in an isolation tree, whenever we go deep, we need to decide as to have what is the baseline that we are considering for, having a reference point, having an idea what a normal point looks like. Because if we know what normal looks like, then we can decide what an anomaly is by comparing them. That is why we, divided by C of n in our anomaly score formula. See, to compare, to normalize the value. Okay, that is the intuition right here. Okay, now what does this result mean? We need to have some interpretation of this result as well. So this H here is basically, it stands for the harmonica series, the harmonic series. So the harmonic series for any value I, it increases like this. Okay, this is like how the harmonic series scales like, and the eventual value looks something like log base 10 I plus gamma, and this gamma is the Euler-Mascheroni constant. Okay, so the point here is that this is very important to interpret, and this term right here 2n minus 1 upon n is like the correction term that we have on our hands. Okay, so it is used to get an idea about what is correct or not. Okay, so now very important, the interpretation of this. So when I, let me write it again. So this term, the first term, this basically is saying that average path length grows logarithmically as n increases. Okay, so nothing complicated, very simple to figure out. Like I said, this h can be approximated to this right here, ln I plus gamma. So the gamma is a constant value, so maybe you can ignore it, no need to consider it. But if you look at the log term right here, you can see that as n is going to increase, this value is also going to increase. So as the path length increases, our tree basically grows logarithmically. So if the tree is increasing, the path length is going to increase, and by how much? It is going to increase logarithmically. Okay, so this is basically a typical result. We know that a binary tree usually increases by the scale of log itself. Okay, what about the second term? The second term is equally as important. So this is the second term that we have got. Okay, so this is basically the sample correction term. This stands for sample correction term. Okay, and what it's saying is that if this value of n scale to something like infinity, let's say the sample size is like a huge value, then this will basically come out to be -2. Okay, so this basically corrects the samples for very high values of n and for very low values of n. So if we have a very small n value here, if this n is a very small value, then the tree is going to be shallower than pure logarithmic growth. Okay, so this is very important to interpret as well. This is the sample correction term. Okay, so this Cn is very important to understand. It is basically taking into account two things. The first is the sample correction term, which is like a correcting term. It is important to understand this. And the first one is how the path length is going to grow when the tree is increased. Okay, and that path length basically grows according to the log formula that we discussed right here. Okay, like if you want to see it, this is how the tree is growing, right? This is how any general binary tree grows. This is how it grows like. See? Like this. All of the nodes are filled. See? So if this is the root, okay, uh, there is one node here, two here, 4 here, then 8 here. Okay, so they are growing by log. Okay, that is what it is. So this was it for the model physics and for how this entire model works. Like, this is very very important to understand. Basically, if you know about the intuition of how this is working, you will be able to move on forward with it. Now let's check out the repo very quickly. Let me go back to the repo and then we'll discuss the coding part. So this is the repo. You can read it. Basically whatever we have discussed is given in the repo as well. So we will look at the data in a second. So this is how the data is looking like. One very important thing, when we'll do the EDA in this, which I'll show in just a second, we can see that the fraud values or the anomaly values are very less. See, 99.8% values are normal, 0.17% are the frauds, which means that the anomalies are this much. Okay. We implement our typical pipeline. This is boring. We have been doing this till now. We start from the EDA and so on. Okay. Properties of anomalies, you can read them. See, the first one, anomalies are few. The second, anomalies are different. By the way, the link of the GitHub bio is going to be in the description. You are very welcome to check it out, and for the code as well. Okay. So this is, we have discussed the two models that we have, distance based and clustering based, and why they basically fail. Okay. This is the EDA, basically plotting a graph for the time versus amount. You can check it out. This is very important. So this gives us the amount, distribution of the amount feature in the EDA, and it is a right skewed distribution, highly right skewed. See, it is extremely skewed towards the right. So we actually do some pre-processing here. I'll discuss this in a second. Look at the ratio. This is the anomaly ratio. See, the fraud values are in, like, they are less than 0.5%. So small values, and this is the normal rate. Okay. If you want to read about the physics and the architecture of isolation tree, it is discussed here. You can read all of this. Let's quickly check out the code. Okay. So typical code, these are all the imports that we have made. This is how you import the isolation forest. It is imported from the ensemble because it is a collection of different isolation trees. Okay. These are all the metrics that we have used. Don't worry, I'll be discussing them in a second. So you can download the CSV file, and basically, you can put these files here. Then you can copy the path and paste it right here in order to use the model. This is all because fraud transactions have nothing to do with time. Frauds are present in the past, present and future, all three of them. Okay, so they don't usually change with time. That is what we wanted to check here, which is why we plotted amount and time here to check how is that how are the fraud values, how are the amount values being affected with time. And we saw that it is a highly right skewed model. Now, as we know, typically what happens is that in a sorry yeah so as we know, in a typical tree based model, we don't usually require scaling, right? In the decision tree, random forest, all of these models, we never required any sort of scaling. We never used standard scaler or anything else, and the reason was simple, because the feature scale did not affect how the splits were created. The splits were rather created on separate algorithms, and in this case there is no algorithm to create the splits. Okay, the only thing we are doing is we are making random splits. Yet we have applied scaling to the amount. Okay, so this is like an exception. Why are we applying scaling to the amount? The reason is because this data for amount is highly right skewed. Okay, so this is going to basically skew the model too much, and it is not going to be good building a model with this sort of values. So we try and scale it, bring the values to a comparable scale, and for the first time we are using a different scaling technique. So this time we use something called as RobustScaler. Okay, let me quickly show it to you. This is how you can use the RobustScaler. So the point is similar. We are doing scaling to bring it to a comparable range, but standard scaler used mean and standard deviation. You know, the formula of x minus mu divided by sigma that we have discussed so many times. RobustScaler uses the concept of median and interquartile range. I repeat, it is using median and interquartile range. Now, why are we using robust scalar here? The thing is that in standard scalar, mean and standard deviation, both of those values are highly susceptible to outliers, right? So the mean values can increase too much when there is a very high value, and they can decrease too much when there is a very low value. So that basically causes an issue. We need something that can counter that negative effect. So for that we go for something which doesn't really care about outliers. Even if there are outliers in the model, there is no issue. Median handles that, because median is basically the middle value. Okay. Similarly, the interquartile range as well. The interquartile range is basically based on percentiles. Okay. So like the 25th percentile and the 75th percentile. So the 25th percentile is called as quarter 1, which is quartile 1, Q1. The 75th one is called as Q3, and Q2 is the middle, which is the 50th percentile. Okay, it's very easy to understand. If you want to understand interquartile range, IQR, in detail, I have left another article in the description. You can read about it. Okay, that is how we scale in robust using in this model. That is how we scale in this model using robust scalar. Okay, so so this is very important to understand why we are avoiding standard scalar in this case. Okay, so you can read about this in the repo as well. I have mentioned it. Okay, this is the architecture and intuition. This is very important. Subsampling, why we are not using the entire sample size for making the tree. So we are using a sample size. So the reason number, these are the two reasons basically. These are very important concepts, theoretical concepts for isolation forest. The first is swamping. So the thing is, whenever our sample size becomes too large, the normal clusters are represented by many points in each trees. So whenever we make splits for anomalous points, it creates confusions, because the normal points are too many in number. So the normal point bleed or enter into the anomaly territory. This basically gives us wrong predictions, because our normal point distribution is too large, so it is going to take some of the anomalous points in it as well. Okay, smaller value of the sample size, like we have taken here 256, where our total data set size was very huge. If we check out the whole, this was like the whole size. We took 256, which is less than 1/10 of this. These types of values, they prevent the problem of swamping. Okay, this is very important. The second one is masking. So the thing is that whenever we talk about isolation tree models, we talk in two terms, either local or global. Okay, so whenever we are looking at each cluster, we are talking about the cluster locally, and when we look at all the clusters from the top, we are talking about in a global manner. Okay, so the thing is, when some anomalies, they form part of micro clusters. Okay, and a large value of this sample, like 256 is a good value, but some other large value, it is going to basically hide the anomalies, because the anomalies will look like normal points, but they will look like normal points locally. Okay, when we look at them from a global perspective, they are actually going to be anomaly values. Okay, so this is the problem of masking. When this sample size is too high, it basically hides some of the anomalies value by making them look structurally similar to the normal values. Okay, and this 256 value was used in the original random in the original so this 256 value was used in the original isolation forest paper as well, where both the problems of masking and swamping are minimized drastically, which is why we use this value, and it worked tremendously. Okay, these are the calculations, these are the same calculations that we discussed. You can check them out, how we achieved it them. Okay, this basically explains the anomaly score. This is the table, the same three cases that we discussed. Okay, I mentioned here that scaling is not needed, because first of all, it is a tree based model. It is making random splits based on feature ranges, not really on distances. How different a feature scale is not going to affect this model, but still amount was scaled anyway, because it was right skewed, extremely right skewed. Okay, very important thing in the code, I'll show this to you in the code as well. It is the contamination parameter. So this parameter basically tells the model, what percentage or what proportion of the training data do we have to treat as anomalies, because we need a decision threshold in order to decide what points qualify as anomalies and which ones qualify as normal points. Okay. And usually if you don't write anything, contamination is set as auto, which is the default value, and it sets the threshold at the score value. Okay. Approximately 10% of all the total points get flagged as anomalies. Okay. But sometimes this is very very aggressive for a real data set, because like I said, in a real data set 10% values are not anomalies. Very very few values are anomalies. Like in our case, 0.17 values were anomalies. This means that out of 100, only out of 100, 17 values will be anomalies. Okay. So in these cases where we know that our fraud rate is very very less, we can maybe set it to this known contamination, and this known contamination is nothing but it is the exact observed fraud rate from our training labels itself. So this is like a very accurate setting up of value for this contamination parameter. Hyperparameter tuning, we didn't use grid search CV or anything here. It was too far too complicated. Okay. So we used manually trained hyperparameters, and we of course compared these values. So first of all, for contamination we set the default as auto, and later we set it to our observed values from the training labels itself. Okay. Time complexity, since there are T trees and each sample is built on psi samples, so the complexity will be n log n, and n here is nothing but the sample size, which is nothing but this psi that we have taken. So it will be psi log psi, and this value is very small compared to n. N is this value, 284,807, and psi is 256. So eventually this time complexity comes out to be very small even when it is repeated for T trees. Okay. Space complexity T into psi. This is because psi is the sample size, and the tree only stores the nodes which are present in the tree itself. Okay. So psi into T is the number of nodes that it stores. So this is also pretty manageable. The main comparison metric in this case, the other ones, F1 score, recall and precision, we have studied. PR-AUC is the new comparison metric. Okay. It is basically the metric which is used in the case of highly imbalanced data sets like this one. Okay. Why is this a highly imbalanced data set? Because more than 99% of the values are normal, and only 0.172% of the values are anomalies. Okay. This is why we need a metric that takes into account this massive imbalance. PR-AUC does that. So this was the graph of the PR-AUC. So the higher the value of this precision recall curve, it is considered to be a better value. Okay. Because it means that the recall value is high and so is the precision, which gives us a very very accurate result. Okay. See, you can read some of this as well. This is all typical. Okay. Failure cases, now again, high dimensionality, I think I stated this in the beginning as well. High dimensionality is a big disadvantage in this case, because random feature selection is not going to be as successful as we want it to be when there are irrelevant features. So if we are dealing with a high dimensional data set, then maybe we should apply something like a PCA or something like an autoencoder based method, where we first reduce the dimensionality and then go on forward with applying the model. Okay. See, feature selection or dimensionality reduction helps significantly. So this is one of the ways we can mitigate it. Okay. Clustered fraud patterns, this is also very important. We again discussed this as that many multiple fraud values, they hide with the normal points. Their behavioral patterns are similar to the normal patterns, so they are difficult to identify separately because they form small clusters of their own. So to separate them using creating random splits becomes a big problem. Okay. This can be solved by some cases, but this is still like a major disadvantage that we get. Okay. You can read the rest of them as well. They are pretty self-explanatory. There is no point of repeating these problems. Okay. These are the key takeaways. Let me see if we missed something. let's check out the code once more. Okay, so this is how we have transformed it. Okay, the scalar. So the scaling was not done for the entire data set, it was only done for the amount because it was right skewed. Okay, uh, this is the dependent variable, the independent variable. We needed to classify it so that we can solve it. This accounts for the missing values. Okay, these two. uh, Test size is zero point 0.2, which means 80-20 split, typical. So first we took contamination as auto as a baseline value, and then we gave contamination as the 0.172 value to compare. Training time, inference latency, this is all typical that we do. Okay, so the training time for the tuned model was of course a bit larger, which is expected. Inference latency, again, it is a bit slower for this, but it is all understandable. And of course the values for the tune model came out to be better. Okay, you can understand this graph as well. So I think this is it for the anomaly detection model. Okay, if you didn't understand anything, I urge very much to check out the articles in the description. It has got the link of the original paper for anomaly detection using isolation